we can measure S11 and S21 when ZL is equal to Z0. That is, when your load impedance is equal to the characteristic impedance, then you can find the values of S11 and S21. So that is, say I have S matrix here, two-port network I am considering. So this is your ZL, here you have Z0. So when the properly terminated port 2, this is port 2, right? This is port 2 and this is your port 1. The properly terminated port 2, by making ZL is equal to Z0, then you can measure the values of S11 and S21. So if you want to measure S11, so we have to inject the signal at port 1. Inject the signal at port 1 and measure its reflected signal at port 1 itself. And no signal is injected at port 2. Okay. So to measure S21, we inject the signal at port 1 and measure the resulting signal power leaving the port 2. That is what this S11 and S21, how we are measuring. So to measure S11, inject the signal means you are giving the input. Inject the signal at port 1 and measure its reflected signal at port 1 itself. And no signal is injected at port 2. And to measure S21, so we inject the signal at port 1 and measure its resulting signal power leaving the port 2. Okay, so that is how we measure S11 and S21. The second one is, we can measure, I am considering here two-port network. So that's why we are taking only 4 S parameters. We can measure S12 and S22 when it is possible, when ZL is equal to ZS, or your source impedance is equal to characteristic impedance. Sorry, this is ZS is equal to Z0. That is, your source impedance is equal to characteristic impedance. Say I have two-port network, the same thing, which is having the incident wave and the reflected wave as A1, B1 and A2, B2. Having the characteristic impedance Z0. This is A1, this is B1, this is A2 and this is B2. So this is ZS. When ZS is equal to Z0, okay, and you are not connecting anything here at the port 2. So the properly terminated port 1, you are terminating the port 1 here, okay. The properly terminated port 1 can measure the values of S12 and S22. So how to measure this S1? So you have to inject the signal at port 2 and measure the signal power leaving the port 1. Okay, so inject the signal at port 2 and measure the signal power leaving the port 1. Okay, to measure the value of S22, you have to inject the signal at port 2 and measure its reflected signal at port 2 itself. So no signal is injecting at port 1. So this is how you are making the measurements of S11, S21, S12 and S22 in the two-port network. Now we'll see some benefits or advantages of S parameters. So what are these advantages? So we said instead of the 4 parameters, that is Z, Y, H and ABCD parameters, we are going to instead, we are using the S parameters which are specially defined for the microwave networks. So what are the advantages? The first one is ease of measurement. So it is very easy to measure these values at high frequencies compared to open or short circuit current and voltages. So if you are using these parameters, you have to go for open or short circuit method, right? So if you are using S parameters, there is no need of doing any open circuit or short circuit as in case of voltage and current measurements. So it is very easy to measure. The second one is S parameters are used to extract. So these are also used to extract transmission line parameters such as your R, L, G, C, Z naught, all those things. Using these S parameters, you can define, you can extract all these parameters. So what are the other advantages? This is the third one. The return loss, reflection loss, insertion loss, the gain, VSWR, reflection coefficient, and other parameters of the microwave network can be derived using S parameters. Okay, the fourth one is it is very easy to convert S parameters of S matrix to the parameters such as Z, Y, H, and ABCD. The conversion is a very easy. Conversion is very easy if you consider the S parameters, that is from S parameters to you can convert this to Z, Y, H, and also the ABCD, and that is also very easy also. Okay, so these are the advantages of your S parameters. So though it is having many advantages, it is also having some disadvantages. So what are the disadvantages of your S parameters? Okay, so the first one is S parameters are useful only in frequency domain. If you are doing a frequency domain analysis, then only these S parameters are very useful, but not in time domain. You can ask, ma'am, we can do the analysis in frequency domain and then convert it into time domain. But if you are considering the S parameters, conversion between this time domain and the frequency domain also it is very difficult. If you do it also, it induces error. Conversion between from one domain to the other domain induces error. The third one is it is not possible to describe the microwave network in terms of both the frequency and the time. Sorry, it is not possible to describe the microwave network in terms of both the current and the voltage. So you can't describe the network in terms of current and the voltages using S parameters. Nowhere you can use the values of voltages and currents. You can't describe the values of these using S parameters. So these are the disadvantages of using S parameters. So the next topic is you're having the properties of S parameters. Okay. the properties of S parameters. So the traveling waves with associated power when scattered out through the ports at the microwave junction can be defined by S parameters. So what are S parameters? So the traveling waves which are associated with the power when scattered out through the ports when the microwave junction, at the microwave junction. So those are defined by the S parameters. So till now we have discussed the S parameters for two-port network, multi-port network, correct? Now we'll see some properties of these S parameters. So these S parameters are square matrix which gives all the combinations of the power relationship between the various input and the output ports of the microwave junction. So wherever you are saying the S parameter, that means you are referring to the power relationship between the various input and the output ports of a microwave junction. Okay, and one more thing is these S parameters do not use open or short circuit conditions. It will not use open or short circuit condition to characterize a linear electrical network. Okay, so if you are so for Z, Y, H and ABCD parameter, we used to consider open or short circuit conditions. But here, wherever you are considering these parameters, there will not be using open or short circuit. Okay, instead we'll be using matched loads. Instead, we'll be using matched loads. Okay, and one more property you can say is these are not properties. You have the other mathematical equations also. We here just we are saying about the physical properties, you can say. So S parameters changes with the measurement of frequency. That is, with frequency the S parameters also it changes. Okay, so if you are considering the S parameters, frequency is must to specify. Okay, so frequency must be specified for any S parameter measurement. In addition to the characteristic impedance or the system impedance. So it is important to mention the characteristic impedance and the frequency also. So without these two, you will not be able to find what is a S parameters. It is must. You should know the value of characteristic impedance and the frequency. So why? Because the S parameters changes with the frequency. Okay. So we are discussing four properties of the S parameters. The very first one is zero diagonal elements for perfect matched network will be equal to the diagonal elements for perfect matched network is zero. That is the first one is zero diagonal elements for perfect matched network. That is, you can write SII will be equal to 0. That is, for an ideal input network with the matched termination, SII will be 0. Since there is no reflection from any port, you can write SII will be equal to 0, or you can also say under perfect matched condition the diagonal elements are 0. So if you are having a network which is terminated by a matched load, then you can write the diagonal elements is equal to 0. The second property is symmetry of S. We are considering here symmetry of S matrix for reciprocal network. That is, you can write it as Sij is equal to Sji, where I is not equal to j. If you consider I is equal to j, then it becomes a diagonal element. So Sij will be equal to Sji, where I is not equal to j. Let me take this as equation 1. So which results in S transpose will be equal to S. So this is what the symmetry for S for a reciprocal network. That means Sij will be equal to Sji, which results in S transpose will be equal to S. So for a reciprocal network has same transmission characteristics in either direction of pair of ports and is characterized by a symmetry of scattering matrix. Okay, so how we can prove this one? So this equation means that reciprocal device or network has same transmission characteristics in either direction of pair of ports and is characterized by a symmetry of scattering matrix. Okay, so we'll see the proof how we can prove this one. For a reciprocal network with the assumed normalization, you are assuming the normalization. So for the assumed normalization, the impedance matrix equation, sorry, the impedance matrix equation is given by V is equal to Z into I. This I can write it as Z. I can be written as A minus B. So this in term you can write it as A plus B, or if you simplify this one, you can write this as Z into A minus B, which is equal to U into A plus B. The same equation you can write it in the other words, or I was just say this U represents your unit matrix. This equation reduces to this one. Okay, Z into these two. This is equal to this one, no? This equation is written here. I've just multiplied here this one with a unit matrix. Okay, then you have to multiply and then simplify. So you'll be getting this equation. I'll just write here. Z into Z plus unity matrix multiplied by B, which is equal to Z minus unity matrix multiplied by A. Let me take this as equation 3. Okay, here U is what? Unity matrix. And we know the S matrix equation. That is, you can write it as B is equal to S into A. Correct, no? So B is reflected wave is given by S into A. So let me take this as equation 4. So compare equation 3 and 4. Comparing equation this 3 and 4, you can write S is equal to this S is equal to, you simplify this one, I'll write one more equation, wait. So this equation 3 can be written as equation B, matrix B is equal to, this is Z minus U divided by Z plus U into matrix C. Now it is very easy to compare this equation. This equation 3 and this equation 4 you compare. So what you can write, S is equal to, S you can write it as, it is Z plus U inverse into Z minus U into A. Correct, na? So this is equation 5. I am comparing equation 3, this equation 4 and this equation 3. So by comparing, I got this S is equal to, sorry, this A is not there. Comparing, you are writing only S, no? So S you got it as Z plus U inverse into Z minus U. So from this I can write the transpose. So what I got for S is equal to, I got, it is Z plus U inverse into Z minus U. Correct. So I can write S transpose from this. That is, what is S transpose? Z minus transpose into Z plus U inverse transpose. And we know that the Z matrix is symmetrical. We have shown this one in the beginning. That is, Z matrix and Y matrix are symmetrical for a reciprocal network. So we can write it as Z minus U transpose is equal to Z minus U. Correct? So if Z plus U transpose will be equal to Z plus U matrix. So therefore you can write S transpose equal to Z minus U into matrix Z plus matrix U transpose. Correct? So let me take this as equation 6. So now I can write S transpose is equal to S. This is what you are wanted to prove, right? That is what your property is. That is symmetry for a reciprocal network. The S matrix is symmetrical for reciprocal network. You wanted to show Sij is equal to Sji. That is nothing but your S transpose is equal to S. So we had started with the matrix equation, that is impedance matrix equation. V is equal to Z into I. So I can write this I as A minus B. That is current in your two-port network is nothing but your incident wave minus the reflected wave they have taken. So this you can in terms write it as A plus B also. Okay. So if you go on simplifying this, you'll be getting one equation, that is your equation 3. Okay. So now you compare this equation with the S matrix equation. So you'll be getting the equation for S. So by using the symmetry of Z matrix, you can write these two equations. That is your transpose will be equal to this one. Correct? The same thing you can apply for S also. That is what you come up with the result. So you have two more properties, that is unitary property, and one more is phase shift property, that we'll discuss in the next class. Now time is up, so that too we'll discuss in the next class.